reagent takes place. Now, the book doesn't talk about adding the second molecule of alcohol, so we won't worry about that. But later, if they come to next semester, they're going to revisit that reaction, and they're going to add alcohol instead of water. But just remember, pretty much anything that HOH can do, water, HOR can do, and alcohol does about the same thing. So you can add H to one carbon, OH to another by these reagents, or instead of using water, if you use an alcohol here, you can add, for these two anyway, and OR. Instead of sodium hydroxide, NaOR, you can add HOR. So keep that in mind for next semester, that you use alcohol, OR minus, and get OR here and OR here. All right, but for now, let's just do the water one. Okay, that's the one you'll see, this chapter, that's the one we're focusing on. So if you do these reactions with this, you would expect 2 moles of water to add. If you have 2 pi bonds, here you have 1 pi bond. But what happens is, you're going to get 1 mole of water added. If you use these reagents, what you get, the first 2 reagents, you're going to get this initially. I'm trying to make sure I can write this correctly. I'm not sure I do. You get this. That's McCartney combination. And that's if you're using these reagents. Let's call these reagents A, or these reagents B. So A or B can be added. First you get this, but before the second mole can react and add, this rearranges. This is called an enol, because it's got a carbon-carbon double bond, so it's an alkene, but it's got an OH, so it's an alcohol. So they call this an enol. Enols aren't stable. So what happens is, this is going to flip up here, and this will flip over here. I mean, you can flip it the other direction, I just had enough space. So this rearranges. Did I do that right? Yes. And so you have this. That's a little curveball, unexpected. You don't get 2 moles added. Okay. So how do you remember what's going on? What's the trick to this? Here's the trick. You have an alkene, just the carbon has most hydrogens, give it a hydrogen. The other carbon, give it the OH. Okay? Or if it's anti-McCartney combination, the carbon has a fewer hydrogens, gets the hydrogen, the other carbon gets the OH. However, if it's an alkyne, here's all you do. Notice the difference between this picture here and this picture here. Look at the difference. We're still adding water, okay, but this carbon gets both hydrogens, and this carbon gets the oxygen double bonded to itself. See? So if you use reagents A or reagents B to an alkyne, you don't get 2 moles of water added. You add 1 mole, it immediately rearranges, and you get a ketone. This is a ketone, okay? Now, I'm not going to ask you for the arrow pushing. Just remember, if you see this, and you add reagents A or B, just give the carbon has the most hydrogens, give it both additional hydrogens from the water, and give the other carbon that has fewer hydrogens, give that to the oxygen. See? So that's how you can keep that straight. So it's a little bit different with alkynes. Most of the time, with 2 pi bonds, you can add 2 moles across those 2 pi bonds. But if what you're trying to add is water, you can't do that. You can only add 1 mole. Before that second mole of water can react, it rearranges. Okay. So, you try to keep that in mind. Now, what about this guy? What about if I start with the same material, and let's call this reagent C. I add reagent C. Well, now I'm going to add a mole of water, okay? The carbon has the most hydrogens doesn't get the hydrogen. It gets the OH. And the other carbon gets the hydrogen. See, so this is anti-McCombin coefficient. Yes?
The one on the top, or in the middle at this point, the most carbons gets the carbon, you said, correct?
The most carbon, the one that carbon has the most hydrogens gets the hydrogen. See, so this carbon here has two hydrogens.
Right.
This carbon, I'm talking about the double bonded carbons.
Right.
This carbon has one hydrogen. So let's draw out the complete structure of the product here. So this would be the product, see? So most cases when you add H something, the carbon has the most hydrogen, it gets the hydrogen, the other carbon gets the something else.
Okay. And that's just the opposite.
Unless you add these reagents here,
Okay.
then it's anti-McCombin coefficient. The carbon has the most hydrogens, doesn't get the hydrogen, it got the OH. And the other carbon got the hydrogen. So, but if you got to guess what they call McCombin orientation. The carbon has the most hydrogens, gets the hydrogen, and the other carbon gets the other group. So if you're adding, let's go back to this real quick. If you're adding HCl, HBr, HI, HCN, HOH, or HOR, typically the carbon has the most hydrogens, gets this hydrogen, and the other carbon gets this group here. Okay. The only exception so far that we've seen where you get anti-McCombin orientation is if you use these special reagents right here, you reverse it. This carbon doesn't get the hydrogen. It gets the OH, and this carbon gets the added hydrogen. So if you use these reagents, same thing happens again. You add a mole of water. The carbon has the most hydrogens, doesn't get the hydrogen, it gets the OH. The other carbon gets the hydrogen. Now, before that second mole of water can add, this is going to rearrange, okay? This is the enol, it's not that stable. So what happens is, this is my pivot point. This swings down here, this swings up here, and you get the rearranged product. And this is an aldehyde. Okay? So look at the difference, look closely now. In both cases, you cannot add 2 moles of water to an alkyne. You can only add 1 mole. And the way the addition works out, when everything, the smoke clears, one carbon, one of these 2 carbons, gets 2 hydrogens. The other gets an oxygen double bonded to itself, see? So in this case, this carbon gets the 2 hydrogens from the water, and this carbon gets the oxygen from the water. Okay? That's McCombin orientation. In this case, with these reagents, this carbon, the carbon has the most hydrogens, gets the oxygen, and the other carbon gets the 2 hydrogens. So basically, when you start with a triple bond, you get one of these carbons ends up with 2 hydrogens, the other double bonded to oxygen. So you just got to try to remember, which works. Okay. Now again, this works with an alcohol. Instead of having NaOH, if I have NaOR, you'd have an R here and an R here. But they don't talk about that in this chapter, so we won't worry about it. We'll just do water across the carbon-carbon triple bond. So that's the first exception to the general rule. The general rule is you have 2 pi bonds. You have a triple bond. In general, you can add 2 moles of something across the triple bond. But you can't if you try to add water. 1 mole adds, rearranges, and you're done. Okay. So that is, let's go back to this. That's one of the exceptions, okay? This you can add 2 moles, this you can add 2 moles, this you can add 2 moles, 2 moles. This we won't worry about, that's the alcohol. This one is an exception, okay? This one you can only add 1 mole. So like if you use chlorine, you can add 2 moles. If you use HBr, you can add 2 moles. Hydrogen gas in a catalyst, you can add 2 moles. But not water. Okay. Can you add 1 mole of this? And the answer is yes. If you add a catalyst, the first mole adds slowly, the second mole adds fast. You can't stop that second step. But you can poison the catalyst. You can add materials called poisons that slow down the catalytic behavior. It doesn't make it as an effective catalyst. You can stop at the stage where you just add 1 mole of hydrogen across a triple bond. See? So typically, here's what you'll see. Typically, if you have a carbon-carbon triple bond, and you add just hydrogen gas and a catalyst, you're not going to get a stop. You're going to have to go all the way to an alkane. But if you add hydrogen gas and a poison catalyst, is that it?
Yeah.
You're going to get this. You know what? Let's address this up a little bit more. Let's put another carbon here in your notes. And these are going to be cis. It's not really shown very well here. The addition is cis. Okay. So how do you poison catalyst? There's a bunch of ways to coat a catalyst with a substance that kind of slows it down. There's a catalyst called Linmar's catalyst that uses quinoline and palladium and sulfate. There's others that use nickel and boron. So, you know, if you just see the word poison catalyst or Linmar catalyst, then you know that something funny is going on. Let's see where they show you this. It's on page 465. Okay, typically, add hydrogen gas and a catalyst, platinum, palladium, nickel. It doesn't stop here, it keeps right on going, okay? I want to stop at this stage, we're going to poison the catalyst, okay? So they can use Linmar's catalyst, it's, you know, quinoline and palladium and sulfate, and that's just a solvent. There's other things somewhere, nickel boron complex. There's a bunch of, you know, if you just see the word Linmar catalyst or poison catalyst, that means you're taking this and making this. So the hydrogens add in a cis fashion. Okay? So you gotta remember that. You don't get the trans isomer, you get the cis isomer. So sometimes you don't want to make an alkane. Sometimes you want to make an alkene. So you want to stop at this stage here. So you can kind of slow down the catalyst. You guys are too young to remember when I was growing up, you could buy leaded gasoline. It increases the octane rating of gasoline. But then they came out with catalytic converters that convert automobile exhaust into less toxic exhaust vapors. And they use, I think, platinum in your muffler as a catalyst to break down the complex hydrocarbons into simpler, less toxic ones. But lead would coat the platinum and it would poison it. It wouldn't do its job. So that's when when I was growing up, everybody bought leaded gasoline. Then they had these catalytic converters. So then you had a catalytic converter, you had to buy unleaded gasoline. And to make sure you didn't use the wrong tank, they had a small opening so the leaded gasoline pump wouldn't go in. You know, I'm using the wrong one. Then they outlawed lead in gasoline because it's really toxic. You know, lead exhaust going everywhere. So, and plus everybody has catalytic converters now. Okay, so now gasoline is unleaded. But anyway, lead would poison the platinum and coat it and make it not as effective. So you can slow down a catalyst by adding something that coats it or does something to slow it down, and that's called a poison catalyst. Anyway, so that's what you want to remember. Now, suppose you want to make the trans isomer. Suppose you want to start with this and make not the cis isomer, but the trans isomer. And you want to stop at the alkene stage. Can you do this? And the answer, of course, is yes. You can add sodium metal and ammonia. And if you add sodium metal and ammonia, you get a complicated series of steps that only adds 1 mole of hydrogen across here, so you end up with an alkene. And the addition is trans. The hydrogens that are added in a trans fashion. So that's kind of nice. Chemists can take a carbon-carbon triple bond and destroy it completely, add an excess of hydrogen in a catalyst, and get rid of the pi bonds. Or they can just take away 1 pi bond, get a trans isomer by adding sodium metal and ammonia, or they can add 1 mole of hydrogen gas in a cis fashion by adding a bit more catalyst. This mechanism that takes ammonia and sodium metal, it's a free radical mechanism, a bit too many arrows. It's not that common a reaction. But anyway, I'm not going to ask you for this particular mechanism because there's too many arrows. 1, 2, 3, 4, 5, 6, 7, 8, too many for me. Anyway, but that just kind of shows you how you go from an alkyne to a trans alkene. So there's a nice little summary here of what you can do. And these are discussed in chapter 12 again, how to do multi-step organic synthesis. This is on page 467. It kind of summarizes ways to add hydrogen across a triple bond. Now, by the way, with alkanes and alkenes, the angles are 109.5 for alkanes. So alkanes overall like this. This is 1, 2, 3, 4, 5 carbons. And alkenes, the angle is 120. So to do this. This is again 1, 2, 3, 4, 5 carbons. But with alkynes, the angle is 180 degrees. So if you have 5 carbons, and say a triple bond, don't do it like this. See, because these are all in a straight line, these guys here, because the angle is 180 degrees. And then you might see something like this. See, so this is 1, 2, 3, 4, 5. Okay, so don't get confused. It's just notation that they use. And so when you see this, you got 1, 2, 3, 4 carbons. If you have more carbons, you start doing zigzag. It's alkane or alkene. But for alkynes, they draw it all in a straight line because the angle is 180 degrees. Anyway, take a look at this. Starting with an alkyne, if I just add hydrogen gas and a catalyst, no special reagents, no poison, I can't stop at this stage here. I go all the way to an alkene. No pi bonds left. On the other hand, if I want to stop at this stage or this stage, I can add hydrogen gas and a poison catalyst, Lindlar's catalyst works, or sodium metal and liquid ammonia, and I can get the alkene. And this is the cis alkene, this is the trans alkene. So depending on what you want to make, you have a choice. And of course, you can take any alkene or any alkyne and add hydrogen gas and a catalyst. That always destroys carbon-carbon double bonds. If you add hydrogen gas and a catalyst, you destroy pi bonds. Okay? So you can go from left to right. You can also go from right to left, and that's what we'll talk about some in the next chapter. And in chapter 12, they'll talk about how to go back and forth. Okay? You already know how to go. Actually, I think they talk about it there somewhere. Let's see if they show you. We can go in every direction except you can't go right now. You don't know how to go from here to here, or from here to here, or from here to here. But you can go to the left, or you can also go from here to here. Right? From here to here. First, add halogen. Second, add a strong base, sodium amide. That will take you from here to here. And then halogen to this, you get this. Just put in some hydrogens. And now you do a double dehydrohalogenation, step 2. So step 1, you do this. Step 2 will give you this. Right? So you know how to go from left to right and from here to here, from here to here. Chapter 12, 11 will show you how to go from here to here. So we haven't gone that direction yet. Okay, so that takes care of adding hydrogen gas. Okay, let's start next to that guy, because you can add hydrogen gas in a catalyst and you will get an alkane, but there's some extra reactions here, and that's what we're talking about now. You can stop it at the alkene stage, okay? All right, and there's only one more reaction in this chapter, and it's the cleavage reaction. Okay, so remember the scissors that you can snip, you can use to snip. Usually when you use ozone, you get snip pi bonds. So if you have carbon-carbon double bond, and you add ozone, followed by dimethyl sulfide, you get to snip this bond, turn the carbon-carbon double bond into carbon-oxygen double bond. Okay? So do the same thing with triple bonds. Just like with triple bonds, you get an extra oxygen that reacts. I don't know if they give you a mechanism. Maybe not, maybe. But if you have this, and you add ozone in the first step, followed by using water in the second step, you get to snip this. So you get this piece, but you also get another OH. So these give you aldehydes and ketones. These are called carboxylic acids. Okay. So, and they don't usually know these mechanisms very well. They probably, they may even tell you that it's not well understood. Let's see if I can find it. Oh, 8477. Okay, so just get your scissors, snip out the carbon-carbon double bonds, replace it with a carbon-oxygen double bond and a carbon-OH bond. Now, there's something kind of interesting here. If you have a terminal alkyne, triple bonds in the middle, you get 2 carboxylic acids. If it's at the end, you get a carboxylic acid and carbon dioxide. Okay? Why you get that at the end? Because here's what happens. If you have what's called a terminal alkyne, triple bonds at the end of the chain, if you start with this and add ozone followed by water, you get this. Okay? You also get this. Okay? But this is unstable. This is carbonic acid. Actually, it's not it. I'm missing something here. Oh, let me get another OH here. You get that. Okay. And this is carbonic acid, H2CO3. This immediately decomposes to give you carbon dioxide gas and water. Okay? So just remember, if it's in the end, this turns into carbon dioxide and water. Okay? If it's in the middle, no, you get 2 carboxylic acids. It's in the end. So if you do this reaction and carbon dioxide gas bubbles out of your solution, you know you had a carbon-carbon triple bond at the end of the molecule. Okay. Now, this reaction is not synthetically useful. We're taking a large, complicated molecule, making smaller pieces. So this is useful for structure determination. And so I'll give you products, because that's what chemists, you don't know what they're starting with. They add ozone and water, and they get carboxylic acids and or carbon dioxide gas, and then they work backwards. They try to figure out what was the structure of the original starting material. So you're going to see problems like that. Looks like they don't show you the mechanism. I don't know what it is. Okay, that's fine with me. These ozonolysis reactions are kind of tricky. All right, so add ozone followed by water. Suppose you got this material. So I got that carboxylic acid, it's actually a dicarbon, and I got 2 moles of carbon dioxide gas. 2 moles of carbon dioxide. Where did I start with? Suppose this is all I got. What did I start with? I'm going to assume I start with a single compound, single substance. So it's easy to try to purify the substance. So we just have one compound. Remember, if carbon dioxide is formed in this reaction, that was a terminal alkyne. Carbon-carbon 2 bonds into the molecule. If you have 2 moles of carbon dioxide, you get a carbon-carbon 2 bond at both ends of the molecule.
No, it's that's his.
This first one, hopefully you get something like this. That would give you 2 moles of carbon dioxide and then a dicarboxylic acid containing 4 carbons. Second one would be a ring compound. Although I kind of told you, and that's true, this compound probably doesn't exist. The angle is 90 degrees and carbon
You got the right
to a
thought.
bond the hybridization is SP, it wants to be 180 degrees, so no one's ever made this compound. You'll never do ozonolysis in water and get this compound from an alkyne, just like we did. We created something. Woo! And the last one. Anyway, you have carbon option, double bond, there was a carbon-carbon triple bond at one time. Okay. So start with that, you get those two pieces. Okay, so with ozonolysis, usually you're working backwards. All right, so addition reactions and cleavage reactions, those are the two main reactions of alkyne. Now, there's another one that you want to be aware of. Cannot get a top reaction to go. Those hydrogens attached to sp3 hybridized carbon are not acidic enough, so there's no base glue that can pull this off. You can't add a strong enough base to do this. Likewise, there's no base strong enough to pull this off, but very strong base can pull off this hydrogen, and that very strong base has to be sodium amide. Or sodium hydride. Those are powerful bases, and they are strong enough to pull up this hydrogen. So alkanes are not acidic at all. Alkenes are not acidic, but alkynes are slightly acidic. If you use a very, very, very powerful base, you can rip off the hydrogen. It's got to be a terminal, see? So this is an aryl, right? See? So it's got to be at the end of the molecule. We have a hydrogen attached to this triple bonded carbon. That can accommodate a charge. And there's a rationalization as usual for everything in organic chemistry. It has to do with hybridization. This carbon is sp2 hybridized. These electrons are close to the nucleus. Electrons are negatively charged. We have negative charge. And the nucleus is positively charged. The more S character a bond has, the closer that bond is to the nucleus. So sp hybridization has one part S and one part P. This pair of electrons are in sp hybridized orbit. They're close to the nucleus. This negative charge is close to the positive charge nucleus. sp3 has one part S and three parts P. P's are long orbits. So this negative charge is far from the positive center. It's very unstable. If you can get that negative charge close to the positive center, it kind of stabilizes a little bit. So that's the rationalization, after the fact, on page 460, that's used to explain why an alkane with a negative charge, the hybridization is sp3. This pair of electrons with the negative charge is far away from the positive center. That's not very stable. With a double bond, hybridization sp2, this is closer to the positive charge nucleus. That's a bit more stable. But a negative charge on a carbon that's triple bonded, so hybridization sp, this pair of electrons in the sp orbital is close to the positively charged carbon center, and so it's more stable. Now, it's not very acidic. You don't think of hydrocarbons as being acidic. Alkanes, no. Alkenes, no. This is just too unstable, this is too unstable. But for alkynes, this terminal hydrogen can be removed only if you use an extremely strong base. Sodium hydroxide won't do it. If you put lye on one of these compounds, take acetylene, you you add sodium hydroxide or lye to the 70, it's not gonna do this, okay? It's just not gonna happen. You have to add an extremely strong base like the amide ion or the hydride ion, so sodium amide or sodium hydride, that will take away this hydrogen and make that, okay? So that's another reaction. Alkynes are very, very, very weakly acidic. So if I give it alkyne and this base or sodium hydride, then just tell me that the base has pulled off the hydrogen from that triple bonded carbon. That can happen. Okay? Otherwise, no. Okay. Now, you learned that negatively charged nucleophile is a very powerful nucleophile, and it can attack the carbon center in an SN2 type reaction. So for instance, if you had a nucleophile that's negatively charged, and a hard X, where X is a halogen, this just comes in from behind, you get a substitution of SN2. Okay? And so the nucleophiles we've seen, you've seen OH minus, OR minus, halogen, let's just put X, cyanide. Cyanide really exists. Okay. So those are some of the sulfide. So those are some of the nucleotides you've seen, and you know they react with alkyl halides, where X is a halogen, and you get direct. Matter of fact, in the lab, some of you have done this lab, some of you have not. There's a few amount of Wednesday class, they made my Wednesday class here. We haven't done that for this reaction yet. But in the lab, we took iodide and butyl bromide, and you made butyl iodide. Take the lab. And this is an SN2 reaction. We exchange one halogen for the other. Okay? All right. So, can you give me the product of this reaction? It's a two-step process. We're going to start with this. Step one, we're going to add sodium amide. Step two, we're going to add CH3CH2Br. Can you give me the products, or the organic product of this reaction? That's all I care about. The inorganic products, so the heck of it, this, but I just want the organic product. First reaction is an acid-base reaction. The second reaction is an SN2 substitution. Again, this is what chapter 12 is for us to focus in on multi-step synthesis, where reactions you learned before, you will string together. Final product, a good point is the final product would be this. after the first step. This is the acid, this is the base. The base pulls off this hydrogen. So after the first step, you're gonna get this. It's like the cyanide ion, carbon, triple bond, something, animal here. And then this protects this carbon, bromine leaves, and you get your final product instead too. Okay, so they're starting to string together reactions. Okay. Any comments, questions? Tired? Sick of this? One minor point that we have to mention. Somebody would here. See this reaction with uric acetate and water, followed by sodium borohydride? That is back in chapter 9, I guess. Yeah, that's in chapter 9. This is overkill. If you have a carbon-carbon triple bond, you don't need to do all this. It's a double bond, yes. If it's a carbon-carbon triple bond, you could just add, instead of mercuric acetate, you can add mercuric sulfate, ammonium sulfate, and sulfuric acid, and water. So don't be too alarmed. Those are reagents you will see. If it's an alkene, they use mercuric acetate and water, followed by this in the second step. But if it's an alkyne, they just add mercury sulfate, sulfuric acid, and water. They don't need this in the second step, and they can get additional water. I mean, they could do this, but this is an acid mercury. So with the alkene double bond, they do have to do this. With an alkyne, just mercury sulfate, sulfuric acid, and water, and they get 1 mole of water added across. So it's a little bit simpler, slightly different. If you see the mercury compound, that's the key. You can add water across the pi bond in carbon fashion. Okay. All right, so they summarize the wheel of misfortune again on page 482. They summarize, they name these guys. They only have a mere 12 reactions. Most of these reactions are addition reactions. Okay. Here we're adding 1 mole of hydrogen, 2 moles of hydrogen, 1 mole of hydrogen, 1 mole of water. No, this is cleavage. This is the cleavage reaction. Okay, we're breaking this into 2 pieces. Okay, so that's different. Here we're adding 2 moles of halogen. Again, 1 mole of halogen too. Be careful. Here we're adding water in an anti-McCormick fashion. Here we're adding, so instead of using mercuric acetate, they use mercury sulfate. Okay. Here we're adding HX. Here we're adding 2 moles of HX. Here we're adding, what are you doing here? Oh, they went the other direction. They're making an alkyne, double dehydrohalogenation. So here, this is production. This is elimination. Step reaction number 1 is elimination. You're eliminating hydrogen and halogen to make an alkene. Reaction 3, 4, 5, 6, 7, 9, 10, and 11, and 12 are addition. So they're all addition reactions except reaction 8. We're skipping this. That's a cleavage reaction. Reaction 1, we're doing elimination to make this. We're going toward this. All the other reactions way. So remember, there's only one easy way to make an alkyne, only one way to get to this point, start with this. But then alkynes, then you go to these addition reactions. Now, another minor point that you realize, these are minor points. If you have a carbon-carbon double bond, you can add BH3 and THF in step number 1. Step number 2, you add sodium hydroxide and hydrogen peroxide, and you get addition of hydrogen and OH. Okay? Notice if it's a triple bond, instead of using BH3, they use BHR2. Okay? It's just a minor little difference. Okay? BH3 is too reactive for a triple bond, so it's a carbon-carbon triple bond. Instead of BH3, what they'll do is take away 2 hydrogens and add 2 R groups. Okay, in the first step. They don't need tetrahydrofuran. This is not as nasty to work with. This is nasty. So they don't need tetrahydrofuran. And then step 2 is the same, sodium hydroxide and hydrogen peroxide. So the key is, if you see, boron compound followed by hydrogen peroxide and sodium hydroxide, it's going to be addition of water across the pi bond in anti-McCulloch fashion. Okay? So the reagents aren't exactly the same for alkenes and alkynes, they're pretty close. The mercury compound is used for both alkynes and alkenes. The boron compound is used for both alkynes and alkenes. Okay, just slightly different. Okay. All right. You want to start the next chapter?
Yeah, let's do it.
Get rowdy.
Leave nothing. Yeah, well, we can't do much, but that's good. The next chapter is a short chapter also. Okay. So radical reaction, and we get a short chapter.